Good morning all. Some PIC microcontroller stuff, specifically a PIC microcontroller on a demo board flashing some LEDs. Yay! So I'm doing some software experiments for the calibration function for my solar charge controller. The problem is, in brief, this thing takes current from a solar panel, puts it into a battery and regulates it so that the battery doesn't overcharge. That's what it does. The problem I'm having is that the little regulator, which is that thing there, voltage regulator, they have a tolerance, so they're not always very accurate. It's not always exactly 5 volts. It can be a bit above or a bit below. And that means that the charge controller is measuring the battery voltage incorrectly because that 5-volt regulator is used as the voltage reference. So what I want to do is, for every unit that is manufactured, not that I'm going to be manufacturing these, but for every unit that's built, you can apply a calibration to compensate for any error in the voltage of that voltage regulator. And there are going to be 2 versions of this solar charge controller going forward. The little femto, which is surface mount and very, very tiny, and an all-through hole version, which will be approximately this size, possibly a little bit narrower. So what this charge controller needs is a calibration value which will be stored permanently in E²PROM. Now this is a slightly different variant of this chip. This is the 12F683. The 12 signifies that it's a small 8-pin chip. This is a 16F690. It's slightly more advanced than the 683 and it's got a lot more I/O pins, but essentially they're very similar microcontrollers. So I'm doing some development on this because I just happen to have it. So yes, this calibration value is stored in E²PROM. Which means that if I switch this off, the calibration value was 1111 or 15 in hexadecimal, 15 in decimal, F in hexadecimal. If I switch the power back on, that calibration value is read out of the first location in E²PROM, written to the lower 4 bits of port C, and then there's a mechanism just to flash the LEDs on and off. In fact, what it's actually doing is switching the port pins from outputs to inputs. So when they become inputs, of course, the LEDs don't light. When they're outputs, the LEDs do light. But the value that came out of E²PROM is written to port C and it's just left there. So that value never changes. It's F. Switch this off. It's F. Unhook this wire. It's F. Scratch this wire in here so that we get lots of glitching. Which means that we're going to get power on resets, but we're also going to get some brownout resets. I think I've enabled the brownout reset on this chip. Brownout just means that VCC doesn't go completely off so that you get a power on reset, but VCC dips to a certain voltage and then the chip will go, oh, don't like that, and it will reboot. So that calibration value is completely stable in the E²PROM. But what happens when you've just built one of these things? You find out that the voltage regulator is not exactly 5 volts and you want to change the calibration value. Well, you can do that by pressing this. So that's 0. Can't see that one. That's 1, 2, 3, and so on. So what this button allows me to do is to pull the calibration value out of E²PROM. It increments it. So that's 4 goes to 5. It writes it back into E²PROM. So if I take the power off, that 5 stays in the chip. So this allows me to change the calibration value. I can cycle round, well, as it is at the moment, 16 different values. And that will allow me to offset any error on the voltage regulator. Now, bear in mind that this can be either high, above 5 volts, or it could be low, below 5 volts. So these 16 values will need to have a certain number above and a certain number below for bringing this thing into alignment. But this button allows me to change the calibration value. What's this button? Well, it's simply connected to the master clear input of the chip. So this is the reset button. So what's the difference? Resetting the CPU by removing power, putting it back on, and the CPU boots up, goes through its reset, and doesn't change the calibration value. And resetting the CPU by pressing the reset button, which is connected to one of these pins in here, master clear, what's the difference? Well, the difference is the chip has a bunch of status bits. So you can interrogate those status bits and you can say, how was I reset? And actually there are 4 ways to reset these microcontrollers. Power off, power on, the brownout, in other words, having the voltage dip, and so it ignores that one. If it sees a brownout reset, it won't change the calibration value. Then there's the Watchdog Timer. If the Watchdog Timer times out and the CPU resets, again, it still doesn't change the calibration value. But the 4th option, Master Clear, or the reset button, that one does change the calibration value. It's now 6. So how do you determine how the MCU was reset? Well, there's a bunch of status bits. POR, BOR, that's power on reset, brownout reset. TO, which I think means timeout, and PD is power down, but they're a bit misleading, those names. They're older, and they're inherited from the first set of PIC microcontrollers. These were added later on. So it's a bit of a mess. And one thing you can't do is directly check for a master clear reset during normal operation, because all 4 of these bits are marked as unchanged. Well, it's very difficult to test a bit to see whether it was not unchanged, or no, you can't do it. So what it ends up having to be is that you have to check things in a sequence. You check first whether it was a power on reset, which means that POR bit would be low. If not, then you check whether it was a brownout reset, which is the BOR bit is low. If neither of those conditions is true, then you can check for a Watchdog Timer reset, which means that the TO bit is a 0. And if none of those 3 conditions is true, then the default is that it must have been a master clear, because none of these 3 conditions is true. So here in my code, I do these tests in order. I test PIC on to see whether it was a power on reset. If it was that power on reset, then of course we don't want to modify the calibration value. So I go to main, which jumps down here, and it misses out this section, which increments the EEPROM data and writes it back to the EEPROM. The second check is, was it a brownout reset? If it was a brownout reset, again, we skip over the changing of the calibration value. Was it a Watchdog Timer reset? Yes. If it was, again, skip over this lot. And then the default, or the remaining condition, if it wasn't any of those 3, then it must be a reset using the reset button, the master clear input, and then that just drops into this, which does increment the E2PROM data and write it back to the E2PROM. And there's this sort of complex write sequence that you've got to issue so that you're absolutely certain that you want to be overwriting your E2PROM. So I now have the ability to set a calibration value, change the calibration value and have it written to E2PROM, and not corrupt that calibration value in normal use. Now, normal use would be that someone will connect this to a battery, and then they'll disconnect it, and then they'll connect it, and then they'll disconnect it. So they'll just power cycle the thing. Brownouts are very unlikely to occur on this unit because it's powered by a 12-volt lead-acid battery, which is regulated down to 5 volts. So the likelihood of that 5 volts dipping to, I don't know, 2.5 volts or something is highly unlikely. I'm not even sure I've enabled the power on reset detect in the charge controller. I can't quite remember. Watchdog timer resets could happen. They shouldn't, but they could. And the Watchdog timer is enabled in the charge controller so that if it locks up for any reason, maybe there was a lightning strike nearby, bit of EMP, chip locks up, Watchdog timer carries on counting, overflows and reboots the CPU. That reboot, you don't want it to corrupt the calibration value. So as with a power on, it won't corrupt the calibration value. But for setting that calibration value initially, when you first build one of these things, you press the master clear. Those 3 questions are asked. Is it power on reset? Is it brownout reset? Is it Watchdog timer reset? None of those. So it must be the push button reset, and the calibration value increments to the next number. So I have the ability to set the calibration value, that's now 9, and hold the calibration value in the chip and not corrupt the calibration value. but how do I actually implement it? How do I put it in the code in the charge controller to slightly offset the A to D reading to compensate for an error in the voltage on the voltage regulator, which also doubles up as the voltage reference for the A to D converter? Well, I think I found a place to put it. So looking now at the charge controller code, now this is quite a long file, but there's a subroutine here called ADC read, and it's what it sort of says. It's the analog to digital converter read subroutine. So it sort of does some setup and then starts an A to D conversion with the chip in sleep. So the chip completely shuts down, all the digital parts of the chip shut down, but the A to D converter, the successive approximation process, carries on running, and that you get a quiet A to D conversion, which means it's less prone to error. That's how it works. But there's this thing here. Now, I'm not going to explain what it is because I had forgotten, and I had to sit and think about this for hours last night to try and work out what it is. But suffice to say that at this point, I subtract 180 hexadecimal from the A to D result register. Now that's 10 bits. So it's split across a low byte and a high byte. But the very first part is simply to subtract 80 hexadecimal from the A to D result low register. Now that's quite convenient because if I put my calibration value on this 80, this is at the moment a constant, so it's just a fixed value. But if I allow that to drop down to say 7F or 7E or 7D, or stay on 80 or go up to 81, 82, 83, that should allow me to slightly offset the value that's come in from my A to D conversion. And that here, I think, is where I'm going to actually implement the calibration offset, and that should slightly tweak the A to D result and therefore change the set point voltage on the battery when it's at float voltage, when it's fully charged, and so that you can keep pressing the calibration button and get it to be exactly 13.5 volts. So I think the stage is set for me to put the calibration code into the charge controller, which means there won't be a button. I suppose I could put a button on the through-hole version. That'd be quite handy, wouldn't it? Perhaps I'll put a place on the PCB. I'm designing a PCB for the through-hole version. Perhaps I'll put a place for a button on there. Could be quite novel. The stage is set, yeah, for me to implement calibration. It can be done on here. It's slightly more tricky. There's the chip, and you've got to connect pin 4, which is in that corner, over to ground. So you'd have to sort of get a piece of wire and prod it on there. And just keep prodding it on, go around all 16 values until your 13.5 float voltage was as accurate as it can be. That's all good and ready to go. Now, just finally in this video, I just wanted to show you what happens if I allow the Watchdog timer to time out and reboot this CPU. Let's change the code to do that. So in my Calibrate on Reset program for the 16F690, the Watchdog timer is actually on, so it's running. But down here in my loop, and this is where I just switch the port C pins between inputs and outputs to flash the LEDs, you can see that every time around the loop I've got this clear Watchdog timer instruction, which means that the Watchdog timer never times out. It never reaches its maximum count, and so the CPU is never reset. And of course that's what you want. You don't want the Watchdog rebooting the CPU constantly. But if I comment that out with a semicolon, then the Watchdog timer will time out. And I think it takes about 4 or 5 seconds to count up to its maximum count. That is modifiable. You can change that somewhere. I can't remember. But I'm going to let the chip time out, and we'll see if we can actually see that. So I need to save that. And, oh, I need to get the programmer out. Yeah, here's the USB cable from my computer. Here's the programmer. I'm using the PIC 2. Not a genuine one. I think this is a clone. Yeah, that's right. The genuine microchip PIC 2 was black. Yeah. Now I believe you can power the board from both an external power supply and this. I think there are diodes. I hope there are, because I don't want to blow anything up. But I should be able to plug that in and thus program this chip. Actually, I'll turn the power off here. Now I need to turn the power on the PIC kit. Oh, I need to do that on screen. So how do you do that? Program, I've got to select the programmer first. It's the PIC kit 2. It tells me that it's found a 16F690 and it's ready. Has it powered on the target system? No, because I need to take off the thing that holds it in reset. So that's fine. Now I need to quick build this, quick build it. Make sure there are no errors. These are warnings, these are messages about registers not being in bank 0, but I've dealt with all that. That succeeded. Let's program the microcontroller. So what's happening here is that the Watchdog timer is enabled and I'm not clearing it. So it is timing out every 4 or 5 seconds. Now I'm going to just bring this camera down. Look at this LED. Let's get my pointer. You can see that it's flashing at a regular rate, but then every now and again it just seems to stay on a little bit longer. And that's the Watchdog timer timing out. So this chip is actually rebooting every few seconds because of the Watchdog timer. But it's still not corrupting the calibration word because I'm explicitly checking for the Watchdog timer. Let's actually take that out of the code now. So to do that, I need to go to my checks for the various status bits about, let's get rid of that output window for the moment, about how the chip was reset. And this one, status, 4, is the test for the Watchdog timer reset. I'm just going to comment these all out. Comment that out, comment that out, comment that out. So no longer is it doing a Watchdog timer reset check. So if it wasn't a power on reset and it wasn't a brownout reset, it's going to assume that I've pressed the reset button, even if I don't. Let's see what happens to that. Project quick build. Make sure that all works. Yeah, that looks good. Program the chip. Make sure that all works. Okay, let's take a look at the board. And now you can see that it is, the Watchdog timer is timing out. It's counting up to its maximum count. It's rebooting the chip. But because I'm no longer explicitly checking for Watchdog reboots, it's saying, oh, well, then that must be a switch reboot. And so every time the Watchdog timer times out, it's changing the calibration value. So, and that's how the code was when I first wrote it. I'd forgotten to put in the Watchdog timer. And so the Watchdog timer was rebooting the chip and changing the calibration value. Well, that wouldn't be very good. That would be a bit of a disaster. Well, I was going to finish there, but actually there's one more thing I'd quite like to do. I'm going to turn off the Watchdog timer, actually in the fuses, in the configuration word. And I'm going to stop checking for brownouts, but I am going to check for power on resets. And then I'm going to waggle these power connections to see if I can create a brownout. I just don't know how easy it is to get a brownout rather than a power on reset. Let's give it a try. So in here, let's get rid of that output window. I want to comment out the PCON 0, the test for brownout. So let's comment that out. Semicolon, semicolon. So now it only checks for power on resets. It won't change the calibration value if it's a power on reset, but it will change it if it's a brownout reset. Can we waggle the connections and get the calibration value to change? I just need to turn off the Watchdog timer. I'm going to do that in the configuration word up here. So I'll change that to off. I'll save the file, why not? So quick build that, which assembles the file into hex code, and program the chip. Has it worked? I think so. So here it is. It's flashing the calibration value, which is currently 1, 0001 binary. There's no watchdog, that's been disabled, so it's not timing out through watchdogs. But can I get it to change that calibration value if I waggle the power lines? Not if this is switched off. So let's pull out the programmer and power it up from my battery box. So here's, can we get brownouts? Just by, oh yes, by scratching this wire along there. Yeah, it's detecting brownouts. Because every time it sees a brownout, if I do a power on, poke that in, oops, where's the old? There's the old. So that's a power on, 5, 5, 5. But if I scratch it around a bit, we get a brownout, and it's moved up to 6. Oh, that's just such fun, isn't it? Right, well, that's all I'm going to do today. No, I mean, that's all I'm going to do today. I'm going to go out in the garden now. So, cheerio!